The last little topic of this section is about arc lengths and areas of sectors. And what do we mean by this? So suppose I have a circle, okay, and I've got some angle here, theta, okay, and it's a circle with radius r. I would like to know the measure of this arc length. So the arc that's subtended by the angle. I would also like, eventually, given this, let's say, same angle here, I would also like to know the area of this sector, of this piece of pie. Not like pie the number, but a pie that you'd like to eat, okay? So those are two problems we're going to try to answer here, okay? The first problem, the arc length, is actually pretty easy. Okay, so we're just going to start with that. Arc lengths. Okay. You'll recall, and this is where having our angles in radians is going to become an advantage here. If I've got my angle, to calculate it in radians, I take the length of the arc that's subtended by the angle and divided by r, by the radius, okay, and that's going to give me an angle in radians, okay. So just remember, for example, if you do a full rotation, right, the length would be the circumference, and if we divide that by r, we get 2 pi. So 2 pi radians is a full rotation, right? So we can do this with any arc length. And that's going to tell us what L is in terms of theta and r. It's just theta r. So this is our first formula here. We can add it here. L is theta r, theta times r. Okay? But it's important that the theta, for this to work, theta is measured in radians. If it's measured in degrees, that formula doesn't work anymore. In radians. So the formula is super simple if it's in radians. If it's in degrees, not as simple. So this is why in mathematics we tend to prefer to measure angles in radians in general. A lot of the formulas that we have, especially those in calculus, they become quite easier when the angles are measured naturally in radians and not with some arbitrary measure from 0 to 360. Let's do some example using that formula. Okay, so imagine that I'm given a circle centered at the origin with a radius of 7 centimeters, and there's an angle here of 60 degrees, and we'd like to know the measure of the arc. Well, there's a little difficulty here, okay, in the problem, because the angle is given not in radians but in degrees. So the first thing I have to do is convert the angle to radians. Okay, how do I do that? Well, the angle I'm looking for, let's call it theta. Theta over 2 pi is in the same ratio as 60 degrees over 360 degrees. So theta, so this implies that theta is 2 pi times 60 over 360. So this is what this is, 2 pi times 60 over 360. This is like same thing as 6 over 36. This is 1/6. So this is pi over 3 radians. So now I have my angle in radians. I'm ready to use my formula. So L is theta times r, so it's pi over 3 times 7, so 7 pi over 3 centimeters. Which is roughly 7.33 centimeters, roughly. Here's another example. you're given a circle. But this time, you know the angle. So the angle is 2 radians. 2 radians, remember, 1 radian is like 57. 2 radians is, 57 times 2. So it's a bit above 90 degrees. Okay? So this is our angle, and we are given the length of the arc. So L here is 5 centimeters, and you're asked to find the value of the radius. So here's kind of, we just need to use the formula, but instead of solving for or evaluating L, we're evaluating R, so we can just replace the quantities. L is 5, theta is 2, and we're looking for R. So R would be 5 half, and everything matters in centimeters. So it would be 2.5 centimeters. So let's look now at areas of sectors. Okay. Here we go. Here's a circle with radius R. And we've got a sector here. So this is R. This is R again. And we've got an angle, theta. And what we'd like to find is this area here. It's not a triangle, by the way, right? Because right, it has this curvy end. So it's really like a piece of pie. So we can't use formulas for triangles. We technically might, like we could split it like that and try to find this part, but finding this part would just be as hard as finding the area of the entire sector. So it wouldn't help us in splitting the area into 2 parts like that. But what's actually easier is that this is actually a portion of the area of a circle. So the area, I should say, of the disk. Circle is actually the outer bound of the disk. So the area of the disk is pi r squared. Okay, so this is the area of sometimes we say the area of a circle. I like to say the area of a disk. So the area we're looking for, its ratio to the area of a circle is in the same ratio as the angle theta to an angle that corresponds to the measurement of the arcs subtended by a full rotation, right? 2 pi r, that's the circumference of the circle. So the angle compared to the, this is an angle in radians right away, right? Angle in radian, which is right the measure of this arc length, right? When we're working in radians, divided by r, right? So actually, this is not 2 pi r, this is 2 pi. 2 pi, so theta in radians compared to an angle that corresponds to a full rotation, 2 pi, is in the same ratio as the area of the sector to the area of the disk. I could also, if my angle is written in degrees, it would be to the same ratio as theta over 360 degrees. Okay, so depending whether my angle is in degrees or radians. So I can use this formula here to find the area of the sector. So if I'm working in radians, the formula is actually quite elegant. So if I solve for A, it would be theta over 2 pi times pi r squared. So the beauty of working in radians is that these pi's are going to cancel. Okay, so you're going to have theta r squared divided by 2, which is often written as 1/2 theta r squared. That's how it's written in your book. So we get this nice little formula. But again, that only works if theta is in radians. Just to compare, if you try to come up with the same formula in degrees, you don't have this nice simplification that occurs, like your pi is going to stick around. Okay, so you're going to end up with that if you're working in degrees. So so that's why, again, we prefer to work in radians. Things are kind of prettier. So let's go through an example here. So I've got my unit circle, and here's the rotation. It's a rotation of 225, so an angle of 225 degrees. And I'd like to know the area of this sector here. Okay, and the radius is 2 in this problem. Okay, so number one, I'm going to convert, because I'm going to use that, I'm going to convert the angle to 220, or the angle which is 225 degrees, in radians. That's my first step. So 225 over 360 is in the same ratio as theta in radians to 2 pi. So theta will turn out to be 2 pi times 225 over 360. Okay. And we end up with 7.85 centimeters squared.